Okay, today we're going to go through the exercise of the day 19 of the Advent of Code 2021. So this time I'm not going to do it live because I was busy these days and I couldn't do every day of the exercise. Instead I did it offline and now I'm going to explain what I did. Because I think the problem of today is very interesting, but it can take quite some time to implement. So let's look at what is the requirement. The requirement is we're giving a list of points as three values, three coordinates in a 3D space. For example, here we have a value, -1, -1, 1. Another coordinate, for example, is -2, -3, 1, and so on. We are giving a list of coordinates, and every coordinate is associated with a scanner. So we have multiple lists of coordinates, and every coordinate is associated, on every list of these coordinates is associated with a scanner. These scanners represent a volume in the space that is a cube with the side of 1000 units, which means that all these numbers can be between -1000 and +1000. Every scanner represents a cube in space, and the cubes that are covered by different scanners do in fact overlap, and they have often at least 12 elements in common. The problem is that we do not know what is the center of a scanner cube, which means that the coordinates that we see here are all relative to the center of a cube, they're not the absolute coordinates in space. And to make everything much worse, we do not know exactly how is the cube aligned with the space. So essentially we do not know, if we see these three coordinates, we do not know which one is x, y, and zeta. And also we do not know the sign, which means that a +2 could be actually -2, because the cube could be upside down. And the same happens in every axis. So what the problem is asking, essentially, is to find out the absolute position compared to the scanner 0, which is considered the default, the reference one, of all the points. So essentially, we know that some of these coordinates will match some of the coordinates that are in scanner 0 once we calculate their position compared to scanner 0, and some of them will be completely new, and we can add them to the space. We can basically combine all the scanner points, calculate what is the real position of the points in a given scanner compared to scanner 0, and build a complete global map of all the points. The two parts of the problem are asking us to first count how many points are there, and second to calculate the distance between the two furthest points. Which means that in general what we have to do, the problem we have to solve, is to find the position of every scanner relative to the others. This is very tricky. One solution that we can find, and also the problem states that if we find 12 points that are in common between two scanners, so if we find a way to move and mirror and change the axis of a scanner so that 12 points overlap the ones of another scanner, we are fine we can declare that we found the proper position. So let's start by noticing that we can have a finite amount of movements that positions that a scanner can have compared to another, because we know that the offset, the position of a scanner, cannot be more than 1000 units above or below another one in all three axes. And also we know that the way the axes are arranged, can be only one across a limited amount of combinations, because the axes can be swapped between them, but there are three axes, so we can have x, y, zeta, zeta, x, y, and so on, many combinations. But in total there are 3 multiplied by 2, so 6 combinations, and only 8 possible combinations of plus and minus sign. So essentially we have in total 48 ways the coordinates can be swapped between each other and also mirrored, so that we can change the sign, which means we can just go through all of them. So we can go through all the possible offset and swapping of coordinates until we find a way a scanner, the points in a scanner are overlapping with 12 points in another scanner, and at the point we found the transformation between one scanner and the other. So we can transform all the other points and we complete the piece of the map. So let's see how I solved it and some tricks that I found. So first of all, the parsing is nothing special. If you saw the other days, you will immediately understand it. So I have scanners, which is a list, coordinates, which is a set. For every line in the input, I ignore empty lines. If the line contains the word scanner, I know that's the beginning of a scanner, so I add the current coordinates to the list of the coordinates of the scanner and create a new scanner. So I simply append to the scanner's list of coordinates and reset the set of coordinates. Otherwise, I'm reading a coordinate set, so I simply parse the tuple, separate by everything that is not a digit nor the minus sign, and I have all the coordinates in my tuple. So this is the input that I have. Each line either indicates that I have a scanner or indicates that I have a coordinate to add to the set of coordinates in that scanner. The only thing that can go wrong is that since I use the presence of the word scanner to know that I finished seeing a list of coordinates, when I reach the end, I have a list that is not yet associated with any scanner. So I have to manually specify that the last set of coordinates that I have are also part of a scanner, which is just an extra scanner that is not detected the usual way. Then I can call part 1. As I said, what we are doing here is solving a single problem, which is stitching together all the coordinates of all the scanners in a single absolute representation, which is based on the scanner 0. Then part 1 and part 2 simply do this operation and calculate different metrics on the result, but calculating metrics is the easy part. Let's see instead how we can stitch together the coordinates. So first of all, I defined a so-called transformation. So a transformation is simply the operation that we do on a point. There is quite some interesting trickery if you use NumPy, and in fact that's how I will do it normally, but not here because I want to show how the problem is implemented. Essentially, when you have 3 coordinates, let's call them A, B, C, because we do not really know which one is X, Y, Z, so I avoid using those terms. I just call them A, B, C, so we don't assume anything about what are they. What I'm doing now is I want to create new coordinates. Then let's call them A2, B2, C2, so that each one of these coordinates goes to one of them, not necessarily the same. So A maybe goes to B, B goes to A, and C goes to C. So the mapping is 101, but is not the same. And they can also be mirrored, so I can have a minus sign essentially. And I also have an offset, which is essentially a number that is added to all 3 of them. Actually, 3 numbers that are added to the 3 of them that move the cube in the 3 axis. So every time I have a scanner to define what is its position compared to another, I have 2 sets of values. So I have a set of axes which tells me which axis goes to which other axis and whether or not is multiplied by -1, so it's mirrored, and a list of translations, which is 3 numbers that simply tell me how much I have to add to every axis. So this is the transform operation. What it does, it receives a tuple with the original coordinates of a point in a scanner, the axis and translation that represent how the scanner is in space, and give me back another point, which is the coordinate in another system. This operation usually is done with a thing called quaternion, and I suggest to look at it if you like algebra. Is essentially a quaternion is essentially a vector of 4 values. So every coordinate is represented with the 3 values that are its 3 axes, and an extra value which is just the number 1. Why we do that? Because if we do that, we can have a matrix which defines a multiplication between 1 and the offset in a way that is nicer to handle through the usual algebra trickery involved with calculated coordinates and projections and so on. But here I'm not doing that because I want to do everything in pure Python, so no NumPy, just Python. So I created this function which is ugly but works. What it does is it receives the original value. I of course wrote some documentation, you can read it from the code. But essentially it does this. It creates an initial coordinate, which is just 0. Then it goes through the axis, which is going to contain the values 1, 2, 3, and the plus and minus of these values, which is simply saying which axis in the new point corresponds to which axis in the old point, and also if it's mirrored. And then I also add the offset. So I add to the value that I get the offset, which is the 3 values that I have to add, and return this result. So I'm applying this transformation. It's an ugly way. It's not how you do a transformation usually, but it doesn't require any extra library and is very simple to read. Once I do that, I can simply work by brute force. So I can say, okay, I know how to apply transformation to a point. So what can I do? I can, given 2 points, create a function that simply tells me every possible transformation that goes from the starting point to end. To do that, first I create a list of possible axis value. As we said, these values are finite. So I have all the possible combination of mirrored axes. There are 8, because every axis can be mirrored. There are 3 axes, so 2 to the power of 3 is 8. And then I use permutations, which is function present in the itertools module in the standard Python library, so I can use it without installing anything extra, which is simply giving me all the swapped values. So it's getting all of these values, and changing all their relative positions. So I can have all the possible axis rotations and mirroring that are defined by the problem. Once I do, I simply go through all of them. I calculate the transformation applied to the starting point and using that axis, so that specific mirroring and swapping of the axis without any offset, so the offset is 0. And then I can calculate the offset as a difference between the resulting position that I have after this mirroring operation and the ending position, because the offset is simply the difference. So I can calculate the offset as a difference between the axis in between 3 axes. At this point, I assert in fact the result of my transformation is what I have, so I am sure that this function will always return something that is meaningful, and I yield the axis and the offset. So one can call this generator and simply get all the possible transformations that go from start to end. And this already quite solves the problem, because if I have a scanner with a list of points, I can simply experiment 2 points that are in the scanner and look whether what is the transformation that goes from one to the other. Once I do that and I find the transformation that works, I can simply apply this transformation to other points in the same scanner, and I should find at least 12 points, so that the starting point in a scanner with the same transformation gives me the end point that exists in the other scanner. So essentially I have to find 12 matches, and once I do, I found the actual position of a scanner compared to the other, and I can transform all the points. This is this is not very simple, because scanners can have a lot of points. So if you look at this, you can have easily 30 points per scanner, which means that you can have 30 squared combination of points, and for each one of them you have to find all the transformations that go from one to the other, and there are many. And then for each transformation you have to look at the original points in one of the scanners, move them according to transformation, and find whether the new point is in the other scanner. This takes forever. It's not a huge amount, but it will take minutes, even if it's implemented in a nice way. So the problem is that we have simply too many points and we do not know which transformation is mapping which point to which other. So what can we do? I thought a bit about it and I found a way to improve a lot this calculation. The idea is very simple. I have to find some points that I already know can or cannot match with other points. So essentially I have to assign to some of the points a signature, some characteristic of those points, so that I know that if a point has a specific signature, which is some detail about that point and it's part of the space, two points that have the same signature are good matches. So I can try them and see whether that's a match that that makes sense to try. So let's how do I do that? I need to find some operation that gives me a result that is consistent even if I move or translate the cube. So even if the cube is mirrored or moved back, down, up, down, whatever direction, a point should have the same signature. And here I found a very simple trick. There are many ways to do that. The ways I found is to consider a small area of space in, let's say, 100 units compared to the 1000 units of the scanner volume. And for every point, I look at all the points that are in that small area around it, and I calculate their distances compared to that point. And I do a sum or also multiplication or some calculation based on that, based on the distances. Why I do that? Because the distance is not affected by the fact the axis is swapped or the cube is moved around, because the distance is preserved across transformation. So if the distance between 2 points is 3, it will remain 3 no matter which axis I swap or how much I move the cube around, as long as that point is in the cube. So to do that, I define this area, this signature range, which is simply how distant 2 points have to be so that the signature is considered. And here I have a function that, given a set of coordinates, gives me the signature of some of the points. So I go through all the coordinates, and for each one of them, I check whether those coordinates are at a distance from the edge of the cube, so at a distance from the plus or minus 1000 on each of the axes, so that the signature is not affected. Why? Because if I observe a point that is on the edge of the cube, that of the points that are seen by a scanner, calculating the distance of near points is not a valid operation, because there may be points that are outside the cube of the volume that the scanner can see, and if I calculate the distance based on those points, I cannot have the same value that I will see from another scanner that instead see the values that are over the edge. So essentially I have to be sure that the point and all the area that I consider to calculate the signature is completely inside the scanner. And that's what I do here. I adjust an if, and if it's close to the edge, I just keep it. Then I calculate the distance as absolute value on the 3 axes. I don't care about what those axes are, because the distance is not affected by the orientation of the axis. And the distance has to be non-zero at least in one of them, because if it's not, then I'm simply considering the point with itself. I could skip it because really every point sees itself, so it's not affecting the signature. I just do not care, I just want to skip it. At this point, what I do, I calculate the signature of a point as the sum of the distances plus 1. I can do many things. I can also take the sum of distances, multiply the distances, apply any mathematical function. The only thing I care about is that this operation has to be deterministic. So every point will receive always the same, very same signature, which is just a number. And at this point, given a set of coordinates, this function will return a signature. So for every point that is not too close to the edge and is in this set of coordinates will give me a number. And the number is the same across all the scanners, no matter how they are turned around or how much they are moved up or down in whatever direction. So using this dictionary, I can optimize a lot the operation, because I do not need to match all the tens of coordinates that are here, but I can already be smart and start from points that have the same signature. And this makes it a lot faster, like orders of magnitude faster. Let's see how it's used. So first we have the problem of deciding what is the range from the signature. To do that, I simply create a function that tries different signatures. In fact, goes from 5 to 900 with a step of 10. And for each one of them, it shows me how many reference points are found. And I went with 155 because that's a number that maximizes the amount of reference points. If this volume is too low, so if I use such a small volume to calculate points, I may not see anything around a point. And if it's too high, I may not see enough points that are distant enough from the edge to actually be useful. So 150 is a good value for my specific case. Okay, so I find this signature trick, and what I do now is I simply have to use it. So in my code, what I do is I go through all the sets, and I assume that the set 0, so the first scanner, is the reference one. Every position here is relative to the scanner position, so the problem simply says that I should consider scanner 0 the first set of points as the reference one. So what I do, I simply put the position of the scanner 0 in the absolute positions, which is a set of all the points, and the references, so the points that I found using the trick, I directly put them also in the dictionary of absolute references. So I already built a sort of map of the space that contains only the scanner 0. Then what I do is I go through all the other scanners, I find the I find all the transforms that can go between one and the other. So I have to find the reference points, which are here. And once I do, what I have to do is simply, okay, I found two reference points that are the same, and I have to compare them. So I have to find the transformation that goes from one to the other. If I do, I have to simply go through all the other coordinates and check whether I found a matching transformation. What is a matching transformation? Is simply an helper that goes through all the points in one in between one coordinate and the other, and check whether I find a valid transformation. Valid transformation is one that finds at least 12 points that have the same coordinates. So I simply go through all the possible transformations and brute force my way out of this list, with the trick that I can use the signature of the points to speed up a lot the calculation, because I do not need to check every possible combination of points, which can be easily thousands for every possible couple of scanners, so a lot. But I check only the signature points that are actually meaningful. Once I do, I can easily speed up the operation. Notice that this is a sort of bet that I do, because it's very possible that I cannot find any signature point at all, because maybe all the points are close to the edge. And in that case, essentially, I'm working on a problem that is probably not solvable, but I can also invent other transform operations. So I can find points with other characteristics, other ways to calculate a signature. In this case, this algorithm worked very fine, so I could easily get all the coordinates. Once I get all the coordinates, it's trivial to do part 1 and part 2. Part 1 is simply asking us all the coordinates of all the points, so how many points are there, and is simply the length of the set of the coordinates. And part 2 is asking us to find the 2 points for which the distance is maximized, and this is simply a nested for. I go through all the points twice and I find the distances. Every time I find a distance that is greater than the greatest one that I found so far, I increase that value, and at the end of the cycle I return that value, and that is the solution. It's a bit convoluted, but you can simply look at the code and ask me if you have any question. It's complicated, but can be done in small steps. Bye!